All right, so we're going to be going over a circuit problem to find the current through each of these resistors using Kirchhoff loops. So the problem will come as just this black Sharpie box, and then you need to implement your loops and your currents. And I always do these the same, and I'll explain why that makes it a lot easier. So as you can see, I did my loops, my left loop going this way, and my right loop going this way. So we have clockwise for the left side, counterclockwise for the right side. And then for my currents, I have current 1 here, current 2 here, and current 3 here. The reason it's important to note where your currents are going in and out is because of these junctions here. So you have to determine I1, I2, and I3, and whether they are adding with one another or on the other side of the equation. So for example, I1 is entering. As you can see, it's entering the loop because it's going towards this junction. I2 is exiting the loop, and I3 is also exiting the loop. So I2 is going to go like that, and I3 is like that, whereas I1 is going in. So in other words, I1 is equal to I2 plus I3. And this will be important a little bit later, and I'll explain why, but that equation is going to remain consistent as long as you keep your currents in your loops exactly how I have drawn them. And I've found this to be the easiest. One other thing to do right off the bat is we're going to combine these two because they're in series with one another. So because they're in series, you're just going to simply add them. No inverse needed. That would be if they were in parallel, and these two are not in parallel with one another. So we're just going to note that this I3 is 18.2. So let's start with solving. We know that our Ohm's law current equation is change in V is equal to I over R. So we're going to separate this into the left side and the right side. So let's do left side. So what do we have on our left side? Well, we have 15 volts. So volts are being added. That's good. Volts are in this equation. Now, to determine whether the voltage is positive or negative, you look at which way the loop is going. If it's going from low to high, then it is positive. So we're going to start with 15 volts, and that is a positive annotation. For our resistors, we determine whether the loop is going with the current or if the loop is going against the current. If the loop is going with the current, it is going to be positive. If the loop's going with the current, it's going to be negative. If the loop's against the current, it's going to be positive. So in this case, our loop is going this way, and our current is going this way. So they're going the same way, so it's negative. So we're going to subtract 7.5, and that is I2. So 7.5 multiplied by I2, right? Because of this equation right here. And then we're going to do this, look at this resistor, because this is also on this left side, and that's what we're solving for right now. So this resistor, as you can see, I1 is traveling this way, and loop 1 is traveling this way. So this guy's moving this way. So these guys are in the same direction. So this is also negative. So minus 11 for our ohms, and that is going to be I1. Because we're referring this to I1, this is I2, and then these two are as I3, but that's on our right side equation. So just to simplify this, and this is all equal to 0, to simplify this, we're going to have 15 volts is equal to 7.5 I2 plus 11 I1. So that's just by adding these over to the right side of the equation, and we can mess around with that later, but I'm going to leave it at that for now. And then let's just worry about our right side, the right side of our loop. Right side. So let's take a look here. We have no voltage, so because there isn't another voltage over here, we don't even need to worry about the voltage, so we're just going to look at these resistors. Let's start with our 18.2, which is the combination of the 6.2 and the 12. These are going to be known as our I3 currents, and they're going opposite direction, so they are going to be positive. So 18.2 I3. And you can see that adding them together because they're in series worked out fine, because if we did 6.2 I3 and then they're both positive plus 12 times I3, we would combine like terms and we would get our 18.2 I3 regardless. Now there is one more resistor we need to take into account, and it's showing the same thing as it did before. Same way, the current is going the same way as the loop, therefore this is negative. So we're going to subtract 7.5, and that is our I2. And that's equal to 0. So here, now we can kind of be done for now at looking at this electrical current, this circuit. We can kind of be done looking at that. And what we need to take into account is that the little equation we made before, I1 is equal to I2 plus I3. Okay, so as you can see, we have two different equations, each missing two terms. So what we need to do is we need to solve for one term and plug it into another term. So let's start with this left loop. I'm going to keep it here. So 15 volts minus 7.5 I2, and then minus, and notice this is I1. What is I1 equal to according to our equation? I2 plus I3. So let's just distribute that negative 11 in for this I2 and I3, because that is equal to I1. So minus 11 I2, and then minus 11 I3. Okay, so that's just distributing this I1 using this equation to put that negative 11 in. So this is saying the same thing as if we kept it negative 11 I1. So now we see that there are two like terms that we're going to add. So we have our negative 7.5, and then we also have our 11. So that's going to be negative 18.5 for I2. Let's just simplify right here. So 15 volts, and then we're going to subtract 18.5, that's our I2, and then minus 11 I3. So we just combine these two guys, and then these remained constant, or the same as they were before we simplified. Now what we're going to want to do is we're going to want to solve for either I2 or I3. That's okay, because we need to plug one of those. We need to either plug in I3 in terms of I2 or I2 in terms of I3. I think I'm going to solve for I3. So we're just going to go add this to the other side of the equation here, and we're going to go 11 I3 is equal to 15 minus 18.5 I2. And then what we're going to do is our 11 I3, we're going to subtract this 15 minus 15, and that's volts, keep that in mind. And that is equal to, so remaining over here, 18.5 I2. Right? So move this over here, moved this over here, this remained there. Now to solve for I2, we're just going to divide by 18.5. So you can get your calculator out for this. First, I'm going to do 11 divided by 18.5, and we get 0.595 I3. Note that's negative because we're dividing by a negative, and this is going to be positive, so 15 divided by 18.5, and we're going to get 0.811, and that's volts. So I'm just going to circle this. This isn't our answer, but I'm going to circle this for now. So that's what I2 is equal to. So now we can refer over to our right side equation, which has variables of just I3 and I2. But it's perfect because we have I2 in terms of I3, and we'll be able to combine like terms. So let's keep our this is I2 in terms of I3. So this I2 is going to be plugged in here. So we're going to keep our 18.2 I3 the same, so 18.2 for our I3, and then we're going to distribute this negative 7.5 into what we found for our I2. So we got a negative, the 0.595 rounded, times our negative 7.5. So that is going to be added 4.463, and that was I2, I3, because that was distributed here. And then we have our negative 7.5 times our 0.811. So 0.811 times negative 7.5. That is going to give us negative 6.0825. Perfect. So now we have this, and it's equal to 0 again. So this equation, because this is equal to I2, we can plug this in for I2. So that 7.5 distributed to this negative 5.95 I3, which turned into 4.463 I3, and then this negative 7.5 also distributed into a positive 0.811, which gave us this negative 6.0825. Now we can just solve because we have two like terms. So let's do our 18.2 plus 4.463, and we get 22.663 I3. And that is equal to, let's add this to the other side, 6.0825. Now, for our I3, all we do is take our 6.0825 and divide by 22.663. So I3 is equal to 0.268. So this is our answer. So that means our current through this resistor is 2.268. So if you really wanted to find the current through all the resistors, you would just plug it back in to honestly any equation you really want. You can do your left side equation, your right side equation. So like, because we have I3, we can plug it in for I3 here, and we do 18.2 multiplied by our 0.268, which is our answer. And then that's going to be equal to 4.8776, which is equal to, add this to the other side, 7.5 I2. So that makes I2 equal to 4.8776 divided by 7.5. I2 is equal to 0.6503. And then you can do that with all the equations. But basically, the reason you draw your loops and your currents the way you do is to get this equation. It depends if it's entering this first junction or the second junction. This is out, this is out, this is in. So what's in is equal to what's out. So if you change this, you are going to have to change this equation. So that's why I always keep this constant, so that I can have I1 is equal to I2 plus I3, which helps combine missing two variables in each equation to allow me to solve for one. And then just quick rule, if you're going from negative to positive, for the voltage, it's going to be positive. If the current is going with the loop, it's a negative ohms, negative resistance. And then if it's going against, so this one's going down, this one's going up, against is positive. Thanks.